Part of my studio audience for the exam review. All right, so start at the beginning. So as we see on this test, there's going to be chapters 4, 5, and 6, which is going to be a mixture of structure and bonding from chapter 4, and then all topics about reaction chemistry and stoichiometry for 5 and 6. So we'll start with some of the latter topics, the chapter 4 material. Sorry, the former. Give the electron group arrangement and molecular geometry, respectively, for the hypothetical anion SeF3-, so trifluoroselenide. All right, so when we're doing these types of problems where you have to determine shapes of molecules, we of course need a very good Lewis structure as our starting point. So we learned about that in chapter 3. It's technically old material, but it's something we still need to be able to do to be able to handle this. So we're going to count electrons for this compound and draw a Lewis structure. So if we go to the periodic table, all right, so we have selenium is in group 6A. It's in the oxygen column, so it has 6 valence electrons. And then fluorine, which is the other one, is in group 7, so it has 7 valence electrons. So we have one of those with 6 electrons. For fluorine, we have 3 with 7 electrons each. And then we can't forget about our overall charge, which is -1 in this case. So we have another 1 electron there. So this ion is going to have a total of 28 valence electrons that we have to arrange around the central atom in the structure. So we start with the less electronegative atom in the center, which of course is selenium. Fluorine is always an outer atom. We put the 3 fluorines around it with single bonds. We complete their octets. So we're going to add 3 lone pairs or 6 more electrons to each fluorine. And then once we've done that, we've completed 3 octets. So that's a total of 24 electrons, which means we have 4 more left over that have to go in the central atom. So if you're going to answer any question about structure, hybridization, bonding, all of those things, it's important to have at least a reasonably good Lewis structure as your starting point. It turns out for determining the molecular structure or for determining things like hybridization, if you're missing some double bonds here and there, it's not a big deal. But you need to have the correct number of valence electrons, and you need to at least know how many lone pair electrons are on the central atom, because that will be very important for determining the geometry. Now, if we write this out in AXE notation, which is a helpful way to classify these things, we have our central atom. It has 3 atoms bonded to it, 3 fluorines. Those are our X groups. And then we have 2 lone pairs of electrons, so that's an E2. All right, so we have to define 2 different parameters or 2 different classifiers for this structure here. So the first one is the electron group arrangement. So when you see that terminology or anything like that, we're talking about the 3-dimensional arrangement of all of the electron groups around the central atom. That includes the bonded pairs and the non-bonded pairs of electrons. And it's going to fall into one of the 5 basic geometries: linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. So it's strictly determined by the total number of electron groups, or in other words, the value of these 2 numbers here, m plus n, in the AXE notation. Okay, so m plus n. So if we look at this, we have a total of 5, so that's what we call the steric number, and that's going to dictate the electron group arrangement. So if you have 5 things around the central atom, the way they arrange themselves to get as far apart as possible is with a trigonal bipyramidal structure. Okay, so we know that the electron group arrangement is trigonal by a pyramid, so that eliminates some of our answer choices if we're confident in that. And now let's also look for the molecular geometry. So because it's trigonal bipyramidal, that means all of the electron groups arrange themselves in a 3-dimensional shape. Now we need to know the names of all these geometries, because that's how we're going to ask you them on the exam, since it is going to largely be multiple choice for these types of questions. So we need to know what they're called, but to remember them or to visualize them, it's helpful to draw them out as well. So when we do this, we know that the electron group arrangement is trigonal bipyramidal. We also should remember that when you have this type of electron group arrangement, all of our lone pairs that we have will go on the triangular part. So we put 2 lone pairs there, and then the rest of the positions are occupied with atoms. So this then is going to make what we call a T-shaped arrangement. So you do have to remember the names, but they're going to be given to you in the answer choices, and if you can draw them out logically, starting from the electron group arrangement, you can often just tell by looking at it what it is, if you're able to do that. So it might reduce the memorization, or if you have a little bit of a brain cramp during the exam and can't remember the exact name for it, it helps to draw out the structure and just look at what it looks like. So the correct answer then that has both the electron group arrangement and the molecular geometry correct is choice C. So if you see an electron group arrangement, that's going to be one of those 5 basic shapes. And then if you see molecular shape or molecular geometry, you have to take into consideration the lone pairs as well. Was there a question over here? Or did I answer it? Yeah.
On your previous lectures, you said that if the central atom is not satisfied with the bondings that it has made based on the octet rule, it loses one of the lone pairs, and that becomes a double bond?
Almost. So the question was about if your central atom is not satisfied with the octet rule, it loses lone pairs to make double bonds. That would only be the case if it has less than 8 electrons. So in this case, our selenium has 2, 4, 6, 8, 10 valence electrons. It's in the 3rd row of the periodic table, so it's able to expand and go beyond 8 electrons. If it had fewer than 8 electrons, then we would start drawing double bonds, but we always take lone pairs off of the outer atoms and use those to make the double bonds. We don't remove lone pairs from the central atom in any case, okay? So that doesn't really come into play here, and it doesn't really matter for drawing Lewis structures because you're never going to take lone pairs off of the central atom. They always come from the outer atom. Another question?
What would a trigonal, bipyramidal, trigonal planar look like?
So there is no such thing. So the question was, what would a trigonal, bipyramidal, trigonal planar structure look like? That never happens because in the trigonal, bipyramidal electron group arrangement, all of the lone pairs go on the trigonal planar part of the molecule. So the atoms would always go in the other position. So you can never have that combination as even a possibility. Yeah, one more? So the steric number is the sum of these two numbers in the AXE formula. So it's the total number of electron groups, which is atoms plus lone pairs. All right, I think in the interest of time, we should move on. All right, now we want to know, same molecule, what is the hybridization of the central atom? So when you're determining hybridization of any atom, in this case it's the central atom of an AXN type structure, you have to have the Lewis structure, which we already did, and all that really matters is that parameter, the steric number that a student just asked about. So as we determined in number 1, the steric number is 5. And so the way we figure out hybridization is we realize that we have, on our central atom, we have an s orbital available. We have 3 p orbitals. So way back when we talked about atomic orbitals, we know that there's a single s orbital in a given subshell. We know that there's 3 p orbitals degenerate in a given subshell. And then some atoms can also utilize d orbitals for hybridization. There are 5 d orbitals, but they're not going to use any more than 2 of those when they hybridize. So if we have a steric number of 5, we need to hybridize the first 5 of the orbitals in this list, which is sp3d. Okay, so that's all we need to do to be able to figure out hybridization. So if you can count and you can remember sppd, then you can figure out hybridization. So it's not that difficult. Understanding what hybridization is and why it occurs is, of course, more complex. But most of the test questions are just going to be identifying hybridization. So that would be choice C. So the hybridization of the central atom always is determined by the steric number or the number of electron groups. There's a 1-to-1 correlation there because both lone pairs and sigma bonding electrons go into those hybrid orbitals. So you need to know the total number of electron groups, not just the number of atoms. So if you have 2 electron groups, that's going to be sp hybridization. 3 is sp2. 4 is sp3. 5 is sp3d. And 6 is sp3d2. Okay, so the Lewis structure can tell you a lot about the compound once you have it drawn correctly. Yeah. So why can we only use 2 d orbitals out of the 5? It's because nothing ever makes more than 6 bonds is basically the answer. You'll never see a structure that has 7 things around the central atom, so you never need to use more than 2 d orbitals. It's probably not that it's not that it couldn't use more than 2, it's just that it never will because it never has to. All right, any other questions on that? All right, so now we're going on to another bonding theory, molecular orbital theory. So this is a conceptual question about molecular orbital theory. So according to this theory, which of the following will increase the bond order in a diatomic molecule? So we have to remember that bond order is determined by this simple equation here, if we want to think about it mathematically or semi-quantitatively. So the bond order is 1/2 times the number of bonding electrons. So every electron that goes into a bonding orbital increases the bond order by 1/2. And then every electron that goes into an anti-bonding orbital decreases it by 1/2. So we have a minus term for the number of bonding electrons. Sorry, anti-bonding. Ooh. All right, so as I just finished saying, if you have electrons in bonding orbitals, the bond order increases. And if you put electrons into anti-bonding orbitals, that corresponds to a decrease in the bond order. All right, so the bonding orbitals are the ones that are lower in energy and that bring the two atoms together. The anti-bonding orbitals are higher in energy than the atomic orbitals, and they push them apart and decrease the bonding between them. So choice A, adding electrons to a bonding orbital, we're looking for an increase in bond order. So this one will increase the bond order. If we add electrons to a bonding orbital, that will do it. If we add electrons to an anti-bonding orbital, that does the opposite, so we don't want to count that one. So check marks are the ones that are true, and then X's are the ones that are false. Removing electrons from a bonding orbital, so that will also decrease the bond order. So if we have less electrons in a bonding orbital, we're going to decrease the bond order. And if we remove electrons from an anti-bonding orbital, which is choice D, what will that do? That will also increase the bond order, because we have less anti-bonding character. So two of these choices will increase the bond order. All right, so that was just a conceptual question about molecular orbital theory. You very well could see something about that, and the key concepts are that when atomic orbitals combine to make molecular orbitals, you have equal numbers of bonding and anti-bonding orbitals that are going to be formed. They can have either sigma or pi type character to them. So definitely review those concepts as we go forward. So any questions on just the conceptual nature of molecular orbital theory? Okay. So moving on to number 4, another molecular orbital theory problem, but this time we're going to apply MO theory to answer a question about the dioxygenyl cation O2+. Okay, so this is not something we could easily draw a Lewis structure for, so molecular orbital theory will tell us some information that we can't get from the Lewis structure. So even if we don't say according to molecular orbital theory, if you're asked about bond order for a diatomic molecule, or you're asked about number of unpaired electrons, assume that you should use the molecular orbital diagram to help you answer that question. So for the molecular orbital diagram for O2, for anything with two oxygens in it, we're going to mix the two s orbitals with each other to make a sigma and a sigma star. So I'm drawing the whole diagram here, which shows you again how atomic orbitals, those on the outside, mix together to form molecular orbitals. What you really need to know for this type of question is just the ordering of the orbitals in the center, because that's where all the electrons go in the molecule, and that's what's going to help you answer the questions about bond order and unpaired electrons and things like that. So I'm showing the full construction, but you don't necessarily need to have all of that, but it is helpful to understand where they come from. Now in the P block, we also have p orbitals available to form molecular orbitals. So all of the valence orbitals can combine to form molecular orbitals. So from each oxygen, we have 3 2p orbitals, and then 2p orbitals, they combine to make sigma and pi orbitals. The pi orbitals have 2 degenerate orbitals at each level. So there's always 2 degenerate pi orbitals, and then when we go to make the anti-bonding orbitals, there's 2 degenerate pi star and 1 single degenerate sigma star. So we're mixing together 8 atomic orbitals. We make 8 molecular orbitals, and they have this pattern, this order of energy, from lowest energy to highest energy, bottom to top. Yeah?
How come sometimes pi is below sigma?
So how come sometimes pi is below sigma? So it's a complicated question to answer. You should remember, though, that if you're in the first part of the p block, so if you're boron, carbon, and nitrogen, that these two orbitals, the sigma 2p and the pi 2p, switch their order. And the reason that happens is a little bit complicated, but it's because in reality, even though we sort of draw them separately, S mixing with S, P mixing with P, S and P to some extent can mix with each other, specifically the sigma orbitals. So that perturbs the energy of the sigma 2p because it's also mixing with the S orbitals. So that's why that happens in some elements and not others. So you need to remember that there's that change there. For the first half of the p block and the second half of the p block, you reverse the order of these two bonding 2p orbitals. And now where that comes in to be important is if you're determining number of unpaired electrons. It won't affect the bond order, which is what we're asking you here, because all you're doing is switching the order of two bonding orbitals. But if you need to know the number of unpaired electrons, it's imperative that you have the orbitals in the exact correct order. So for this one, we're talking about O2+, so we need to know how many electrons go into this. So each oxygen has 6 electrons, so there's 2 of them, but we have a +1 charge, so we have 1 fewer electron than the neutral atom. So this compound has 11 electrons, and if you try to draw a Lewis structure for an odd electron species especially, it becomes very difficult. So the molecular orbital theory will help us answer this question about bond order. So if we put the 11 electrons in here, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we fill from bottom to top. We follow Hund's rule, Pauli exclusion, just the same as they do for atomic orbitals, and we fill them in that way. So the configuration for this compound, if we were to write an electron configuration, we have 2 electrons in the sigma 2s, 2 electrons in the sigma star 2s. We have then sigma 2p has 2 electrons, so we're working from lowest energy to highest energy, just like we do for atomic configurations. You don't have to write all of this out, but this would be the configuration. Pi 2p 4, so our pi 2p is completely filled. There's 2 pi orbitals, so you can have a total of 4 electrons. And then our pi star 2p has 1 single electron in it. That's the last electron we put in up here. Okay, so with this configuration, we can calculate bond order. So bond order is 1/2. We take the number of electrons in bonding orbitals. So we have 2, 4, 8 electrons in bonding orbitals. 2 sigma 2s, 2 sigma 2p, 4 pi 2p. So 8 of our 11 electrons are in bonding orbitals, and the other 3, the 2 that are in the sigma star 2s, and the 2 that are in the pi star 2p, or the one that's in the pi star 2p. Those 3 electrons are in anti-bonding orbitals, so we get a bond order of 2.5. Okay, so molecular orbital theory allows us to easily predict half bond orders, fractional bond orders, which would not be something that's easy to do using Lewis structures. All right. Questions on this one or any related topic? Okay, moving along. So here we're talking about, so we're onto some new things now. This first one is about atomic mass and the definition. The hypothetical element TT has an atomic mass of 132.2145. Yes, I use that symbol because it's my initials. Forgive me for that. If it has 2 stable isotopes, 131 and 134, what is the percent abundance of 134? So for this type of question, we just need to know the definition of atomic mass and how it relates to the individual isotope masses. So this again harkens back to things we learned much earlier in the course about isotopes, where they're elements or atoms of elements that have different numbers of neutrons in them. And in a real sample, in a natural sample of that element, you're very often going to have mixtures of 2 or more isotopes. And the atomic mass that you get from the periodic table is the weighted average of all of those isotope masses. So it's it's not just one mass or the other. So the average of all of them that are there. So the equation that goes along with this is that the atomic mass for any element is the fractional abundance of isotope A, we'll call it, times its mass, plus the fractional abundance. So fractional abundance is related to percent, but it's out of 1. It's the fraction, not the percent. And the abundance of B times the mass of B. So if you have 2 isotopes A and B, this is the formula. If you have more than 2 isotopes, you just keep going on down the list until you run out of isotopes. So every single isotope, you take its abundance times its mass, and then you add that string of numbers together to get the atomic mass that's reported on the periodic table. So in this particular problem, we have to look at what our given information is and what is our unknown. So our atomic mass is given. I tell you the atomic mass right off the bat, so that's given. And then the individual isotope masses, we have two of them in this case, only two. Those are both given as well. We have 131 has a mass given here, and then the 134 isotope has a mass given there. Okay, so we have both masses are given. So it's always helpful to take stock of what you know and what you don't know. But we don't know anything about the two abundances. We're only solving for one of the two, but we don't know either of them right now. So we have two unknowns in this, so to simplify things, we'll call this x and we'll call this y. So if we have two unknowns, we need a second equation. And remember that the sum of all of the abundances always equals 1, just as the same as the sum of all the percents equals 100. So if you have two unknown abundances, x and y, they have to add up to be 1. We're solving for the abundance of 134, which I'll call y in this example. So let's call that y, so then we can rewrite this as x equals 1 minus y. So if we put those substitutions in, if we use those unknown abundances as x and y, our atomic mass, which is given, 132.2145, is equal to the mass of the 131 isotope, which is 130.9856, times its abundance, which is x, or we can rewrite that as 1 minus y, because we're going to solve for y as we'll see. And then we're going to add to that the mass of the second isotope, 134, which has a given mass of 133.9767, times its abundance, which we've defined as y. So now we have one equation, one unknown. We can solve for y. That's our abundance. So if we do the algebra, I'm not going to work through it in great detail, but we get 0.4109. Now, we have to always, with these types of questions, when we're talking about percents or abundances or fractions and things like that, you have to read the question and ask, see what exactly it's asking for. So we're looking for the percent abundance. So for percent, we need to multiply by 100. If we wanted the fractional abundance, we would stop there. So always, read closely. That's a very common mistake people make, which is to report a fraction when we ask for a percent or vice versa. So don't fall into that trap. So the percent is just that number times 100, which is 41.09%. And as always, when you're entering answers in the blackboard, follow the directions carefully. Don't enter units unless we tell you to. So this one says no units. I don't like going back and manually regrading all kinds of questions because you guys didn't read the directions. It makes me cranky, so don't do it. It's already a busy week for me next week. All right, so that's a typical type of question about the definition of atomic mass and how it relates to isotope masses. Any questions on that? All right, on to number 6. So another part of this test, which is the very beginning of Chapter 5, are conversions involving moles, which of course form a small piece also of stoichiometry problems that we'll see later on. But we'll have some problems that are just that by itself. So we want to know how many moles of sodium ions are present in 65.65 grams of sodium phosphate. So there's a lot that goes into this problem. It's a fairly simple problem overall, but we have to be aware of a number of concepts, a number of things, including things that we learned earlier. So the first thing is, for problems involving moles, you need to know the chemical formula, because very often we're going to use the mass of that or something about that formula to extract information. So if you don't know the chemical formula, you're stuck. So sodium phosphate, we have to convert that to a chemical formula. So sodium is Na+, it's an ionic compound, and then phosphate is this polyatomic ion, PO4 3-. So if we're going to combine those ions to make an ionic compound, it has to be 3 sodiums to 1 phosphate to balance the charge. Okay, so that's the chemical formula for sodium phosphate. And then here we're looking for the moles of sodium ions present in 65.65 grams. So if we're going to convert grams into moles as part of this calculation, we also need the molar mass, which we're not given either. So once we have the formula, we can find the molar mass, which is just the sum of the atomic masses. So we have 3 sodiums. We go to our periodic table. The atomic mass of sodium is 22.99. I'll try to zoom in on that a little bit. 22.99 is the atomic mass of sodium, or there's a larger periodic table, which also has pretty small writing over there. So we sum the atomic masses to find the molar mass of the compound. And then we have 1 phosphorus, PO4, so we go over to phosphorus, has an atomic mass of 30.97. So this is the masses of sodium and phosphorus, and then we have 4 oxygens. We go back to our periodic table. So periodic table is your friend. The atomic mass of oxygen is pretty much exactly 16. So the molar mass of this compound is 163.94 grams per mole, which we'll need. So sometimes we'll give you the molar mass, but it is something you'll still need to know how to calculate in other cases. So we need this parameter. Now we're ready to go to town. So always read closely what the problem is asking you for. We're not looking for just moles of sodium phosphate. We're looking for moles of sodium ions. So the moles of Na+, we have 65.65 grams of sodium phosphate. We want to convert that into moles, so 1 mole of sodium phosphate has a mass of 163.94 grams. But here's where a lot of people are going to stop and forget the last step, which is if we're looking for moles of H+, we look at our chemical formula. Each sodium phosphate has 3 Na+. That's what that little 3 tells us in the formula. So we have 3 moles of Na+ for every 1 mole of sodium phosphate, Na3PO4. So don't forget that last step, and if you do all that, you should get 1.201 moles. Again, if this was a Blackboard problem, enter your answer without units, 1.201. Okay, I'm going to do a quick check to make sure my recording is still going. It is. And any questions on this one or related concepts? Okay, so this is a simple equation involving moles, but remember, if you're asked about moles of atoms or moles of ions, you need to also take into account the chemical formula and what that tells you about the relative number of moles of each element in that formula. Okay, we have to keep moving, so we're down to 1 more hour left before we get booted out of here. Okay, so the next problem. Catechol is 65.4% carbon, 5.49% hydrogen, 29.1% oxygen by mass. What is the empirical formula for catechol? So for empirical formula problems, we need to find the moles of each element in the compound using the information in the problem. So if we're given mass percents like we are here, we assume 100 grams of compound. So we're going to assume 100 grams. Oh, come on. My tablet's taking a little bit of a break, although we don't have time for that. So the question is, assume 100 grams because we're given percents? Yes, because percents mean out of 100. So if you assume 100 grams of compound, each of these percentages tells you how many grams of each element are in 100 grams of compound. So when you're given percent, that's the way you want to do it. So we have 100 grams of compound. So we want to find the moles of each element. All right, this is being, oh, come on. Good job, tablet. All right, there we go. So the moles of carbon, we have, our mass percent of carbon is 65.4. So in those 100 grams of compounds, we have 65.4 grams of carbon. And for these, we're just going to use the atomic masses to figure out how many moles of each element there are. So 1 mole of carbon from the periodic table, we have a mass of 12.01. Okay, that's atomic number 6 for carbon. So So we have 5.45 moles of carbon. The moles of hydrogen, remember for these problems we only want to use atomic masses. So we have 5.49 grams of hydrogen. Hydrogen basically has an atomic mass of 1. If we want to be really precise, it's 1.01. So we get about the same number of moles of hydrogen, and then the moles of oxygen, 29.1 grams of oxygen, because it's 29.1 mass percent oxygen. And then 1 mole of oxygen has a mass of 16 grams. Okay, so those are the moles of each element, and then the empirical formula is just the ratio of those moles. So we could write our empirical formula as C 5.45, H 5.44, O 1.82. Now, of course, we don't write chemical formulas like this with decimals, and those don't match any of the answer choices. So the way we deal with this is we take all of these subscripts and divide them by the smallest one to reduce them down to simpler numbers. So we take each of these and divide by 1.82 because that's the smallest subscript for oxygen. And this comes out pretty exactly to C3H3O. Okay, well, that's going to match choice A. Okay, so there's a couple variations on this, but when you're finding empirical formulas, you need to find the moles of each element. That's the approach you want to take and figure out how to get there. And this is a pretty standard way to do that using mass percent. Okay, questions on this one? Okay. And now another variation on the same theme is determining the empirical formula using combustion analysis. So question 8, we're not directly given masses of each element, or even indirectly. We have to find them out in a different way. So for combustion analysis, we take a compound, we burn it, and then we measure the mass of CO2 and water that forms. So when you burn a compound, all of the carbon ends up in carbon dioxide as a product. All of the hydrogen ends up in H2O. And then oxygen, you're adding oxygen when you're combusting it, and it goes into both CO2 and water. So that one you have to determine indirectly at the end, as we'll see. So we need the molar masses of CO2 and water, which I should have given you. So the molar mass of CO2 is 44.01, and for water it's 18. So I'm not going to, I'll spare you the agony of calculating those, but that's what they are. And we need to find the mass and the moles of each element. Now for a combustion problem, if you have something other than carbon and hydrogen, in addition to finding the moles of each element, you also need the mass, because carbon and hydrogen, we're going to use the combustion data to find out how much of those there are. But then anything else that's in there, in this case oxygen, we have to find at the end by subtracting the amount of carbon and hydrogen from the total mass of the compound. So we're burning 5 grams of compound. That's going to have some amount of carbon, some amount of hydrogen, some amount of oxygen in it, and we need to figure out those amounts. So we have to first start with the mass of each element, because that's going to allow us to find the mass of the one that we don't know. So the mass of carbon, we're told that we're forming 11 grams of carbon dioxide. All of the carbon comes from that. So we can do this type of conversion to get the mass of carbon. So 1 mole of CO2 has 44.01 grams. So we convert the mass of CO2 into moles of CO2. But we're interested in the amount of carbon. So we have, in the CO2, the formula is 1C, 2 O's, 1 carbon, 2 oxygen. So we have 1 mole of carbon for every 1 mole of CO2. But we first need the mass of carbon to get started on this. So we're going to do the molar mass of carbon, which is its atomic mass, 12.01 grams of carbon in 1 mole. So essentially this conversion here allows us to figure out, of these 11 grams of CO2, how much of that is carbon. That comes from the mass percent of carbon, and this is maybe an indirect way of finding that, but it just uses simple conversion straight across. So we get 3.00 grams of carbon in this compound. Okay? Now the mass of hydrogen all the hydrogen in the combustion reaction goes in to make water as a product. So we have 6.01 grams of water. That's told to us in the problem, given to us. So 1 mole of H2O has a mass of 18 grams. And then here's where we have to be careful. So if we want to know how much hydrogen is in H2O, we have to recognize that there are 2 hydrogen atoms per H2O molecule, or 2 moles of hydrogen per mole of H2O, as we're doing it here. So 2 moles of hydrogen per 1 mole of H2O. And then we can use the atomic mass of hydrogen, 1.01, to find out the mass of hydrogen. So we have 0.674 grams of hydrogen. And then finally, we need to find the grams of oxygen, the mass of oxygen. That one we cannot find directly from the combustion information because both of our combustion products have oxygen in it, and a lot of this oxygen came from the air that we burned it in. So for the mass of oxygen, we use the total mass of compound, which is given to us as 5.00 grams. So the first sentence of the compound tells us that we're burning 5 grams of a compound. We just found that that has 3 grams of carbon in it. It also has 0.674 grams of hydrogen, so all the remaining mass must be oxygen, which is 1.33 grams. And now we're at the step where we can do it the same way we did the previous problem, which is take all of these masses for each element and convert them into moles, and then use that to find empirical formula. So there's a lot of steps here in this type of problem, but we're getting close to the end. So the moles of carbon, we have 3 grams of carbon, and we use the atomic mass to tell us that there's 0.250 moles of carbon. The moles of hydrogen are 0.674 grams. 1 mole of hydrogen has a mass of 1.01 grams. So we have 0.667 moles of hydrogen, and then finally the moles of oxygen. We have 1.33 grams of oxygen times 1 mole is 16.0 grams. I'm running out of room here, so this looks terrible. But we get 0.0831 moles of oxygen. Okay, so that step there was just using the atomic masses to find the number of moles. So let's add another page here. Okay, just going to put a page in eventually. Okay, so we have moles of each element. So our empirical formula is going to be C 0.250, so that's the number of moles of carbon we had. H 0.667, O 0.0831. We have to divide these by the smallest number to get a whole number formula. And again, this comes out to whole numbers in the first step. So we get C3H8O. All right, so a lot of steps to that, but in a combustion analysis problem, you're going to use the mass of carbon dioxide and the mass of water to figure out how much carbon and how much hydrogen is in there. And then from there, it's pretty much similar to the types of problems we did before. Okay, any questions on that one? Yeah.
Is carbon always going to be 1-to-1, even when we don't know what the compound is?
Is it always going to be 1-to-1?
Yeah,
For the CO2?
mass of carbon, when you're converting from carbon dioxide to figure out how much.
Well, and the reason it's 1-to-1 is because CO2 only has 1 carbon in it. So it doesn't matter where that carbon is coming from. All of the carbon goes into CO2, and each CO2 only has 1 carbon atom in it. So that's where that 1-to-1 comes from.
It doesn't matter that we don't know what the product says at the
No, because this is not a molar ratio from the chemical reaction. This is a molar ratio from the chemical formula. So it's CO2, 1 mole of carbon, 2 moles of oxygen. We're using the atomic composition, not any sort of balanced chemical reaction to figure out those ratios. Okay? Yep. All right. Anything else? So we got to keep going because we're a little bit behind. All right, number 9. 3.25 grams of butane is burned in the presence of excess O2. We're told the formula is C4H10. What is the mass of CO2 that forms in grams? So this is a standard mass-to-mass stoichiometry problem. We're telling you the mass of a reactant, and we're asking you to find the mass of one of the products. Now we have to realize for this type of problem, and this is one of the types of reactions we have to be familiar with, is that a combustion reaction has a very typical format. So we have our reactant that we're burning, in this case C4H10. The only other reactant in a combustion reaction is O2. Then we always make CO2 and water as our only products. Okay? So when we balance these reactions, we're going to usually set the coefficient of whatever we're burning to 1. We're going to balance the product side first and then balance O2 last. So if we have C4H10, we have 4 carbons, so we need 4 CO2s to form. We have 10 hydrogens, so that means we need 5 waters to form. And then if we look at oxygen, on the product side of the reaction, we have 4 plus times 2 is 8 plus 5. So we have 13 oxygens, which means we need 13 halves O2. If you're repulsed by the idea of fractional coefficients, we can double everything, take the whole thing and double it by 2. So we get 2 C4H10 plus 13 O2 going to 8 CO2. Now, it doesn't really matter if we have fractional coefficients. It's not going to hurt how we approach the problem. And especially for this one, because we're told that O2 is in excess. So really, the coefficient in front of O2 doesn't even matter for this problem, so we're not considering the amount of O2 at all. We need to know the ratio of C4H10 to the product CO2, which is what we're interested in. So it's either 1 to 4 or 2 to 8. Both of those will work equally well. So now we're just ready to set up the conversion. So the grams of CO2 is, we're starting with 3.25 grams of C4H10. In the stoichiometry problem, we convert to moles first. So if we're starting with mass, we use the molar mass. 1 mole of C4H10 has a mass of 58.14 grams. And now we're in moles of C4H10, but we're interested in mass of CO2. So we use the mole ratios. 8 moles of CO2 forms for every 2 moles of C4H10 that react, or we can use 4 to 1 if we prefer. 8 moles of CO2 for 2 moles of C4H10. Now we're in moles of CO2, and just finish this off by converting to mass of CO2, which the molar mass of CO2, which I didn't give you in this problem, should have is 44.01. So we should get 9.84 grams of CO2, which we would enter in as 9.84 in Blackboard. All right, so mass-to-mass stoichiometry, very typical type of problem. Do we have any questions on that? All right, we need to plug along because we're about halfway through with our time and not quite halfway through with the questions. So what is the percent yield of this reaction shown below if 29.6 grams of gold are combined with 50 milliliters of 4 molar HOCl in the presence of excess HCl, and we form or obtain 33.9 grams of gold chloride? So a lot of given information here, we need to know what to do with it. So we're asking for a percent yield, which means we need to determine the theoretical yield, and we're going to also then use the actual yield, which is 33.9. So usually the actual yield is given to you unless that's what you're solving for. So we're told that we're obtaining this much product. We need to figure out what is the theoretical yield, how much of that can form. So in this problem, this relates to some things we just talked about in class today. We have to recognize that we're given masses of 2 reactants. So our balanced reaction is 3 reactants. We're told that HCl is in excess, so we don't have to worry about that. But we're given a mass of gold and we're given a volume and molarity for HOCl, one of our other reactants. So because we have amounts of two reactants, we have to figure out which one of those is a limiting reactant. They're given to us in different formats, but one of them is still going to be limiting and determine how much product can form. And so to do that, we have to find the moles of each reactant and then find the stoichiometric ratio, as we call it, to figure out limiting reactant. So the moles of gold, we're told that we have 29.6 grams of gold. We go to the periodic table. Gold is an element, and its atomic mass is 196.97. Sorry, we're going to divide by that, though, because we're converting to moles. So 1 mole of gold has a mass of 196.97. So we have 0.150 moles of gold, but the quantity that we need to determine if this is a limiting reactant is that number, so we call it R. It's going to be the number of moles divided by its coefficient. So the reaction is given to us as balanced. This is a redox reaction, so you could be able to balance it yourself if we asked you to, but we already have the coefficient, so the coefficient for gold is 2, which means the stoichiometric ratio for gold is 0.075. We do the same thing for HOCl. We have to find the moles first.
How do we know it's 2?
Sorry?
How do we know it's 2?
The coefficient is 2 because that's what's in front of gold in the balanced reaction. So yeah, when we're doing this approach that I used, using stoichiometric ratios, we take moles and we divide it by the coefficient from the balanced reaction, which in this case is 2. So the moles of HOCl, we have to find that as well, but we're not given a mass, we're given a volume and a molarity. So we have 50 milliliters of HOCl solution. The molarity is 4. We have a 4.00 molar solution, which means we have 4.00 moles of HOCl. And as I showed you today in class, an easy shortcut is that's per 1,000 milliliters of solution. So molarity is moles per liter or moles per 1,000 milliliters. So we have moles, and then so that's just a one-step process to get moles of HOCl, which is 0.200. Now this is why it's important to find stoichiometric ratios, because we have more moles of HOCl than we have of gold, but that does not necessarily mean that gold is a limiting reactant, because if we do the stoichiometric ratio for HOCl, we take that number, 0.2, we divide by its coefficient, which we go to the balanced reaction is 3. We get 0.067, which is slightly smaller than the stoichiometric ratio for gold. So this guy here is our limiting reactant. That's the smaller of the two numbers. Now, in reality, this is a stupid way to carry out this reaction because your most expensive reagent is in excess, which is really stupid. But that's what the problem is telling us. So we have more HOCl than we have gold in terms of stoichiometric ratio. So we have to use the amount of HOCl to determine how much product can form. So our theoretical yield is just a standard stoichiometry calculation. We're going to take moles of our limiting reactant. So we're looking for the grams of our product, gold chloride. We take our moles of limiting reactant, 0.200, which we just found above. We convert that into moles of product using the coefficients from the balanced reaction. So 2 moles of gold chloride form for every 3 moles of HOCl. So those are just the numbers in front of them in the balanced reaction. And then the molar mass of gold chloride, we'll use that to convert into grams. So for finding percent yield, we can use either moles or mass as our quantities, but we're given an actual yield in grams. So let's go ahead and find the theoretical yield in grams as well. So the molar mass of gold chloride is 303.32. That's given to us in the problem, so we don't have to calculate it. So when we do this calculation, we get 40.4 grams. So that means 40.4 is the maximum amount of product that can be formed. So that's the theoretical yield that's the yield of the product when all of the limiting reactant has been consumed. And we use stoichiometry to figure out what that number is. So finally, the percent yield then is the actual yield, which is given to us as 33.9 grams, divided by our theoretical yield, which we just determined is 40.4. For a percent, we always multiply by 100, and we get 83.9 something percent. I forgot to write the last decimal out. Let's just pretend it's 0. It might not be. If you, when you're entering, the reason we do answers to 2 decimal places in Blackboard is so that we don't have rounding errors. So if you're off on the last decimal place, especially for a number this big, you're not likely to have problems anyway. So I don't know what that fourth digit is, but 83.90%. So you take the theoretical yield, you put it on the denominator, you divide with the actual yield in the numerator. Okay, questions on percent yield? Yes? Why did I use, sorry?
Yeah, where it says R, H, and CF, why did you use the 0.200 instead of the 0.2?
Okay, so the question is, when I started the calculation down here, why did I use 0.200 instead of the stoichiometric ratio? The important thing to realize about stoichiometric ratios and the place where they're most likely to cause you problems if you're not thinking about it, those numbers are only used to determine what the limiting reactant is. Once you know what that is, you throw those numbers out. You don't use them for anything else anymore. Because that is a molar amount divided by a coefficient. But when we're actually finding the amount of product that forms, we have to start with the actual number of moles of reactant, not with that adjusted amount. So don't use that number. That's the one caveat for doing this approach, is that those numbers that you calculate, once you're done with them, leave them behind and don't ever worry about them again. Okay, good question though. Anything else? All right, moving on. All right, so if 125 milliliters of water is added to 225 milliliters of 0.254 molar NaCl, what is the final concentration of NaCl? Assume volumes are additive and enter your answer with 3 decimal places and no units. Okay, so we're adding water to an aqueous solution. We should immediately recognize this as a dilution problem. So the light bulb should go off in our head, and we should think about M1V1 equals M2V2. Okay, so when we're doing dilution, which is just taking an aqueous solution and changing its concentration by adding solvent to it, or adding it to solvent, whatever the case may be, in that type of problem, we use this equation. So we're looking for what is the final concentration. So essentially we're solving for M2. It could be M1. The definition of M1 and M2 is arbitrary. So we're going to solve for M2, which is M1V1 over V2. Okay, so if we look at the information in the problem, we're told that our starting volume is 225. That's our V1. Our starting molarity is 0.254. That's our M1. So the only thing we need to solve this problem now is V2. So it's important to realize that V2 is the sum of the volumes. It's the final volume. It's not just the amount of water we add. It's the total combined volume once we dilute the solution with water. So V2, if we assume additive volumes, which we're told to do here, 225 milliliters, which is V1, plus the amount of water that we add, 125 milliliters. So our final volume is 350 milliliters. Okay, so the total volume once we dilute the solution. So that would be one common mistake to make on this one. So now that we have these numbers, we plug them in. So our M1 is 0.254 molar. V1 is the initial volume. Now when you're using M1V1 equals M2V2, you don't have to convert your volumes into liters, because in this case, the volumes cancel out. 350 milliliters is our V2. So milliliters cancel out, which means we can use that as our volume. We don't have to necessarily convert. If you convert into liters, you're not going to be wrong. It's just an extra step that you don't need. So with this, we can then calculate the final molarity, which is 1.63 molar. So if you're using the dilution equation to calculate a final molarity, it should very well be smaller than your first molarity, or else you mess something up. You can't make a solution more concentrated by adding water to it. Okay? Questions on dilution equation? Yep.
In order to figure out which one of these substances is the solvent, we should just go for which one has the bigger mass?
So the question is about which one of these is the solvent. So the solvent in an aqueous solution is always water. It's always the pure water. So it doesn't, and then the solute is whatever is dissolved in that water. So it's not really important for this type of problem to make that distinction anyway, but by definition, when you have a solution which is in a liquid, the liquid material is usually classified as a solvent, and then what is dissolved in that liquid is the solute. But that distinction is not terribly important for most types of problems, but that would be the case for this one. NaCl is the solute, water is the solvent. Yes?
What if it wasn't set up where it's like milliliters?
So if it wasn't set up like milliliters over milliliters, when you're using M1V1 equals M2V2, you're always going to have a ratio of two quantities involved when you're solving for it. Those have to have the same units. So before you put them into the equation, you need to make sure their units are the same. Here they're given to you as milliliters, so you don't have to convert them. But when you're doing that, make sure the units always divide out. You're left with molarity, which is the unit that you're looking for. If you're solving for volume, then you need to make sure that the two concentrations that you're dividing are both molar concentrations, which is the standard concentration unit anyway. But all right, so good question, and that's why it's always helpful to write out the units to make sure that they divide out like they're supposed to. Any other questions? Okay, so moving on to number 12. Which of the following mixtures will not form a precipitate? So for these problems, we need to analyze the possible products and know the solubility rules for them. So we're mixing together two aqueous solutions. So we don't even have to write balanced reactions for this. We just need to know what the identity of the products are and predict their solubility. So for choice A, we're mixing KCl and silver nitrate. So we swap the cations and ions. We get KNO3 plus AgCl. AgCl is the world's most common precipitate, so we should recognize that that's insoluble. So this first combination will form an insoluble precipitate. Choice B, we work through the rest. So the first compound has ammonium and sulfate, and we're mixing that with lead perchlorate. So we form NH4ClO4, that's ammonium perchlorate. So two polyatomic ions in combination. And we also form lead sulfate. So if you look at choice B, this first compound here has NH4 plus, which is always soluble, and it has ClO4 minus, which is always soluble. So that one's definitely not going to precipitate. But our lead sulfate, most sulfates are soluble, but when they're paired with lead or silver and a few other examples, those are going to be insoluble. For choice C, we form two products. So for choice C, we're mixing sodium carbonate and barium chloride. So we're going to form NaCl plus BaCO3, barium 2 plus, carbonate 2 minus. And we should recognize that pretty much all carbonate salts are insoluble, so that's going to be our precipitate here. Sodium chloride we should definitely recognize as being insoluble, otherwise the world's oceans wouldn't exist as they do today. Okay, and then the choice D, NaOH plus iron 3 chloride. So the two possible products are, again, NaCl, which is soluble, and then iron is going to pair with hydroxides. And we remember that except for group 1A and 2A, hydroxides are insoluble. So this iron hydroxide will precipitate from this mixture. So far A through D form a precipitate, which means if there is a correct answer, it's got to be E. Let's verify that. So in choice E, we're going to form, we have calcium nitrate and ammonium chloride. We're going to form calcium chloride and ammonium nitrate. And both of these are soluble. So most chloride salts are soluble unless they're paired with silver, lead, or copper or mercury. So both of these products are soluble because the chloride is paired with calcium, which is a soluble chloride salt. Ammonium and nitrate are always soluble, so that one, of course, is soluble. So choice E would not form precipitate if we mix those two together. Okay, questions on solubility rules. This is something I can't really teach you very much other than you just have to familiarize yourself with it. But I gave you the method in class. Look for the obvious ones first. Those cations and anions that are always soluble or almost always insoluble, zone in on those, and then the rest of the little, tricky or hairy ones you have to just spend some time familiarizing yourself with. Okay? Okay, we need to move on. So number 13, a solution has 25.65 grams of calcium perchlorate, and we want to know what is the concentration of perchlorate ions in molarity. So we have to find the formula for calcium perchlorate first. So we need calcium 2 plus. So calcium is in group 2A of the periodic table. So that means it's always going to form 2 plus cations. It's atomic number 20 there. And then perchlorate is one of our polyatomic anions, ClO4 minus. So when we combine these two anions together, we have a 2 plus cation, we have a 1 minus anion. So we need to have 2 of our anions to balance the charge. So the formula for calcium perchlorate is CaClO4, and that's important because even though we're given the molar mass, we're looking for the concentration of perchlorate ions, so we need to know how many of those ions there are in the formula, or we're going to be hopeless. So this is similar to one of the problems we did earlier, but this time we're using molarity and volume, and we're solving for molarity instead of for just number of moles. Okay, so if we want the molarity of perchlorate ions, we need the moles of perchlorate, ClO4 minus, divided by the volume of our solution in liters. So we're told that our solution has 1.23 liters, so we already have the volume given to us, but we need to find the moles of perchlorate from the other information in the problem. So the moles of perchlorate, this is just another mass to mole conversion, but it involves one extra step. So we have 25.65 grams of calcium perchlorate We convert that into moles first by using the molar mass for the whole thing. So 1 mole of calcium perchlorate has a mass of 238.98 grams that's given to us in the problem, the molar mass. But we have to be careful now because we're looking at the problem and seeing that it wants the concentration of perchlorate ions. This will just be the moles of the intact calcium perchlorate, and we should recognize that when this dissolves into solution, we're going to release 2 moles of perchlorate per 1 mole of calcium perchlorate, and that's because there's a subscript of 2 after the perchlorate in the formula. Okay, so we have a 2 to 1 mole ratio of perchlorate to the ionic compound. So that gives us moles of perchlorate. So again, that last step there, doubling the number of moles to account for the number of ions in the formula, is one that's often forgotten. So we get 0.2147 moles of perchlorate. So then we put that into the formula for molarity, 0.2147 moles divided by 1.23 liters, which is the given volume of this solution, and that's 0.175 molar. Okay, so if always read the problem carefully, because if we were asking you for molarity of calcium, it would be half of this because there's only 1 calcium perchlorate. So remember, those ionic formulas tell us how many moles of each ion are released into solution when that compound dissolves, and that's often going to go into calculating the molarity if you want to know the molarity of a specific ion in the compound. Okay, questions on that? All right, number 14, titration problem, which we just went over today. What volume of 0.255 molar HCl would be required to neutralize 125 milliliters of 0.242 molar calcium hydroxide? Enter your answer with 1 decimal place and no units. All right, so we did a problem almost exactly like this in class today. So it's an acid-base reaction, a titration problem, so we need to write the reaction between the acid and the base. So HCl is going to combine with calcium hydroxide. So calcium is Ca2+, so it's going to have 2 hydroxide anions. And that's going to form water as one of our products in an acid-base reaction, and then the ionic compound, which is composed of calcium, which is the cation associated with our base, and chloride, which is the anion associated with the acid. So it's calcium 2+, so we need 2 chlorines to balance that out. So if we want to balance the reaction, we should recognize that HCl has 1 H+, calcium hydroxide has 2 OH minuses. They have to react in a 1-to-1 ratio, so we need 2 equivalents of HCl to react with the 2 OH minuses that are in our base, and then we should also form 2 moles of water if we care about that, though we don't really need that for this problem. So now we just need to find what volume of HCl solution with this given molarity is going to react with that volume and that molarity of NaOH. So we're looking for the milliliters of HCl solution. We know that we have 125 milliliters of our calcium hydroxide solution. So now it becomes a stoichiometry problem. We're figuring out, we have how much of our calcium hydroxide and then how much HCl is required to react with that. So we have 125 milliliters of calcium hydroxide solution. The molarity of calcium hydroxide is 0.242, so 0.242 moles of calcium hydroxide for every 1,000 milliliters of solution. And now we can use ratios from the balanced reaction. So we need to write this reaction out first because we need to know that for every mole of calcium hydroxide that reacts, it requires 2 moles of HCl. Okay, so you need to have at least the coefficients on the left side of the equation need to be correct for you to do this problem. Because we're trying to figure out how much HCl reacts with that calcium hydroxide. It's a 2-to-1 mole ratio. So 2 moles of HCl react with every 1 mole of calcium hydroxide. And then our last step is we're asked for volume of HCl solution. So we're going to work backwards and use the molarity and then convert back into volume. So our concentration for HCl is 0.255 molars, which means we have, for every 1,000 milliliters of solution, we have 0.255 moles of HCl. We write it this way because we want moles of HCl to cancel, and we want to end up in milliliters of HCl solution, which is, the question is specifically asking us for milliliters. So when we write that out, we get 237.3 milliliters. Okay, so for solution stoichiometry problems, if we have molarities and volumes, it's very often possible to calculate one of those using the information in the problem, as we did here. Questions? So we just saw this today, so definitely review it, but at the core of it is just basic stoichiometry like we've learned before. It's just doing it a little bit differently when we're dealing with molarity and volume as our units. Okay. Number 15. In which of the following is the correct oxidation number for nitrogen given? Okay, so here's a little bit of practice determining oxidation numbers. So for an oxidation number, each atom in the compound has its own oxidation number. We only care about nitrogen really, but very often we're going to find other oxidation numbers first. So there's that list of rules I gave you in class that you want to review on, but some elements have pretty much the same oxidation number in almost every compound. So those are the ones we want to assign first. Nitrogen is one in particular that's highly variable, so we can't usually just look at the compound and immediately know what nitrogen is without knowing something about the rest of them. So choice A is nitric acid. So to assign oxidation numbers, we start with the obvious ones. So in a covalent compound, or in an acid in particular, hydrogen is always +1. Oxygen is almost always -2 unless it's bonded to fluorine or itself. And so if we have a +1 and 3 -2s, that's -5, so we need a +5 on nitrogen to balance those out. Remember, the sum of the oxidation numbers equals the charge of the compound or the ion. In this case, it's a neutral compound, so they should all add up to be 0. So that's the only way to get that. So nitric acid is +5. Choice A has it as +4, so that's wrong. We're trying to find the one that's correct. Choice B, NO2. So oxygen is -2. If there's 2 -2s, you need a +4 on nitrogen to balance that out. So choice B is incorrect. So it also helps to draw the Lewis structure. We know that the Lewis structure of NO2, well, it would be complicated because it's odd number of electrons, but it's going to have nitrogen at the center with 2 oxygens on the outside, so no oxygen-oxygen bond, which you need to be aware of. And then finally for choice C, NCl3. Halogens, so in this case, nitrogen is also the central atom because chlorine is more electronegative, and if a formula is written as NCl3, you can safely assume that the single nitrogen is in the center. Halogens in group 7 are usually -1 oxidation numbers, which will leave nitrogen as +3. That's also wrong for choice C. And then finally, choice D, N2. N2 is a neutral element. It only has one kind of atom in it, one kind of element. So that means the oxidation number is 0, not -1. So the correct answer for this question is none of the above. So none of these have the oxidation number for nitrogen assigned correctly. So review the rules for oxidation numbers, and again, zoom in on the obvious ones, which are usually hydrogen, oxygen, fluorine, things like that, which pretty much have the same oxidation number in every compound, and assign the rest from there. Okay, questions on oxidation numbers? So the question is, how do we get 4 on NO2? So for NO2, we want to assign oxygen as -2. That's one that's almost always going to be true, except for O2 and hydrogen peroxide, H2O2. So in just about every compound, oxygen is -2. So if we have 2 -2s for oxygen, we have to add what for nitrogen to get a sum of 0? So it's a neutral compound, so they should add to be 0. So we need a +4 for nitrogen. So that's going to be a +4 oxidation number to balance out and make it equal to 0 when we add them all up. So that's how we got that same story as what we did for part A, which is using the other oxidation numbers in the compound to then deduce what the oxidation number is for nitrogen. Okay, anything else? All right, number 16. When the following equation is balanced, what is the sum of all coefficients? So this is a classic balancing oxidation number problem, and so we need to go ahead and review the method for doing that. So we have, I should have given you a little bit more room so I don't have to write it out again, but we have H plus MnO4 minus NO forming Mn2 plus NO2 plus H2O. So the first thing we have to do is figure out the oxidation numbers of all of the atoms and figure out which ones are changing. So H plus is an ion by itself, so it has a oxidation number equal to its charge, which is +1. MnO4 minus. So this one's a little bit tricky, but we have oxygens, which are -2. We have 4 of them, which is -8. The overall charge is -1, so that leaves +7 for manganese. So +7 plus -8, or sorry, +7 and -8 is -1. NO, I think we saw a similar one above. So NO, we have -2 for oxygen, +2 for nitrogen. Mn2 plus is an ion by itself, so it's going to be +2. NO2, we just did that above, so it's by the same argument I just described, -2 for oxygen and +4 for nitrogen. And then H2O, we see this in a lot of these, is +1 for hydrogen, -2 for oxygen. Okay, so those are all of the oxidation numbers. You want to become adept at assigning those so that you can work through these quickly. And now we can get to the fun part, which is now adding coefficients to balance. So in a redox reaction where the electrons are being transferred and oxidation numbers are changing, we want to start by balancing the number of electrons. So one of our reactants is going to lose electrons, the other reactant has to gain those electrons, and so the electrons that are lost by the reactant have to be equal to the electrons gained by the other one. So we figure out which ones are changing. So manganese goes from +7 to +2. So that's a 5 electron process because the oxidation number is changing by 5. In this case, it's gaining 5 electrons because the oxidation number is decreasing by 5. Although that doesn't, we just need to know that there are 5 of them involved. And then for the other oxidation number that's changing is nitrogen. So nitrogen on the reactant side is +2, and over here on the product side is +4. So going from +2 to +4 is a 2 electron process. Okay? So as we have it written now, with coefficients of 1 in front of everything, we're losing 2 electrons from nitrogen, and we're gaining 5 electrons on manganese. So the number of electrons don't balance out. So we need to adjust the coefficients for that to happen. So if we have a 5 and a 2, the least common multiple is 10. So we have to multiply the coefficients for manganese by 2 to make it a 10 electron process, and the coefficients for NO and NO2 get multiplied by 5 to make that a 10 electron process. So we write those coefficients in. We have H plus 2 MnO4 minuses. So if 2 of those are reacting, that involves 10 electrons. We have 5 NOs. We have to multiply that coefficient by 5 to balance electrons, and we're left with 2 Mn2 plus. So all of the species that are connected by the tie lines that have a change in oxidation number between reaction and products, they get the same coefficients or the same adjustment in their coefficient. 5 NO2s, and then water, which isn't balanced yet. Now the last step is to balance the water and oxygen part, the water and H plus part. So if we look at our reaction side, we have 8 oxygens, we have 5 oxygens from this, so we have a total of 13 oxygen atoms. Over here we have 5 NO2s, which is 10. So we need to have 3 more oxygens, which will come from water. So once we've adjusted the coefficients by balancing the number of balancing the number of electrons, we don't want to adjust these at all anymore. These have to stay, or else we're going to unbalance our electrons. So we need 3 more waters to balance oxygen. And if we add 3 waters, that means we have 6 H pluses. So the sum of the coefficients is 6 plus 2 plus 5, which is 13, plus 2 is 15, plus 5 is 20, plus 3 is 23. So all of the coefficients add up to be 23. So in redox reactions, you're very often going to get a lot of coefficients. They're not going to be trivially small like they are for acid-base reactions. And it's very helpful to follow this method for balancing, because if you just try to guess and check, you'll probably be guessing and checking until the end of the test. It's just not going to work out very well. So use the method, balance the electrons first, and that makes it a much more approachable type of equation to balance. All right, questions on balancing. We do have to hurry a little bit, so we might have to table questions for the end so I can get through everything. Okay, number 17, what is the net ionic equation when aqueous solutions of barium nitrate and sodium phosphate are mixed together? So if we're talking about mixing 2 ionic compounds, we should recognize that it's a precipitation reaction, or potentially a precipitation reaction. So the ions that are present, barium nitrate is Ba2+. So barium is in the second column of the periodic table, so it's going to be a 2+ cation. We have 2 NO3 minuses to balance that. And then the other ions in the other reaction are sodium, which is Na+. We have, and then PO4 3-. So sodium phosphate is Na3PO4, so it's 3 sodiums and a phosphate. The possible products, so we could write out the full equation, but if we're talking about net ionic equations for precipitation reactions, we should recognize that in the net ionic equation, it's going to be the ions that combine to make your insoluble products. That's all we need in this reaction. So if we know what the product is, it can simplify things a lot for us. We don't have to write out all of the entire balanced equation. So the possible products are barium combined with phosphate, which is going to be Ba3PO42, barium phosphate. And then the other product is sodium combined with nitrate. So this guy is soluble. Sodium nitrate is, obeys both those rules. Both of those cations and anions are always soluble. But this is one of our insoluble phosphates. So most phosphates are insoluble, except for if they're paired with sodium, lithium, potassium, things like that. So this is an insoluble product, which means our net ionic equation is going to be just the ions that make up this compound combining to form that insoluble product. So barium phosphate has 3 barium 2 pluses, 2 PO4 3-, and they combine to make 1 insoluble Ba3PO42 barium phosphate compound. So the only choice that matches this is choice E. So choice A has nitrate in it, which is going to be a spectator ion. Choice B has sodium nitrate, which we know are both spectator ions because that's the soluble product. In choice C, this is not an ionic equation because the soluble compounds are not divided up into ions. And then in choice D, this is a total ionic equation because every single ion is listed, including the spectator ions. So I don't have a lot more time to go over that, but review those. And if you know your solubility rules, you can write net ionic equations quickly because it's just the ions that combine to make your insoluble product. Okay, number 18. A sample of sulfur trioxide is found to contain 5.66 times 10 to the 24 oxygen atoms. What is the mass of the sulfur trioxide, ignoring the spelling mistake I made in sulfur? Okay, so this is a standard conversion problem. We're sort of moving back in time a little bit. This is not the most recent stuff. But we're looking for the mass of sulfur trioxide. We're told that we have 5.66 times 10 to the 24th oxygen atoms. So we should recognize that sulfur trioxide is SO3. That's the formula that comes from that name. And we're given a number of oxygen atoms. We haven't used it yet today, but another conversion we have is Avogadro's number. So we're looking for the mass of sulfur trioxide. So we convert to moles first, atoms into moles. We don't have a direct way of going from atoms to mass. So 1 mole of oxygen is 6.022 times 10 to the 23rd oxygen atoms. So that's moles of oxygen, but we're looking for the amount of SO3 that contains this many oxygen atoms. So 1 mole of SO3 would be 3 moles of oxygen. So that comes from the chemical formula again. SO3 tells us that for each mole of SO3 we have 3 moles of oxygen. So if we want to find the amount of SO3, we have to use that conversion. And then the mass of SO3, we're just going to multiply by its molar mass, which I didn't give it to you, but it's 80.07 grams of SO3 for every 1 mole of SO3. And that gives us 250.9 grams. Yeah, I'm sorry. All right, and then, so we're already getting booted. So I think I can finish these really quickly. So, all right, zinc metal and zinc nitrate react to form zinc nitrate and nickel metal. So this is the balanced reaction, 1 to 1 to 1 to 1. So we balance it out, and we don't need any coefficients in this. If excess zinc metal is added to this solution of nickel nitrate, how many grams of nickel are formed? So this is a stoichiometry problem using both molarity and mass conversions. So you have 254 milliliters of our reactant solution. We convert into moles. We need moles of our reactant as the first step. So the molarity is 0.101. So there's 0.101 moles of nickel nitrate over 1,000 milliliters of solution. We're asked for the amount of nickel that forms, so we use mole ratios to convert from nickel nitrate into nickel metal. It's a 1-to-1 reaction, so 1 mole of nickel forms for every 1 mole of nickel nitrate that reacts. Okay, this reaction here is very simple, 1-to-1 coefficients. So now we're in moles of nickel, and then finally get into the mass of nickel. We need its atomic mass, which from the periodic table is 58.68. So we get 1.500 506 grams. All right, so to be respectful to my colleagues who are much higher on the totem pole than I am, I'll do number 20 later. It'll be in the YouTube video, and this will pad my YouTube stats, so it's a win-win. All right. Okay, we're back from our commercial break. Let's finish off this last problem that I didn't get to during the actual session. Okay. So number 20, just another balancing redox reactions problem. We want to know what is the sum of the coefficients on the reactant side when balancing with the smallest whole numbers. All right, so for this one, the first step is going to be to determine the oxidation number. So chromium chloride, Cl is -1 in ionic compound specifically, and this is going to be a +2 cation. So +2 and -1. Nitric acid, we've seen this many times. +1 and -2 for hydrogen and oxygen leaves a +5 for nitrogen. We go to chromium nitrate. So we have 3 nitrates. That means our chromium is +3. And then in the nitrate counterion, oxygen is -2. We have 3 -2s is -6, which means we need a +5 on nitrogen to make an NO3 1- counterion where the sum of the oxidation numbers equals the -1 charge. The other product is nitrous acid, HNO2. So just like nitric acid, +1 and -2 for oxygen. But here we only have 2 oxygens, but we have 2 -2s is a -4, +1 is -3, so that means we need a +3 on nitrogen. In this case, water should be mindless by now, +1 and -2, and then HCl is +1, -1. So acids are always going to be +1 for hydrogen, and then the anions have whatever charge they have. Okay, so those are the oxidation numbers, and we find the ones that change. So chromium is going from +2 to +3. So that's a 1 electron process. And then we have our nitrogen from nitric acid going from +5 2 plus 3 as it converts to nitrous acid HNO2. So this is a 2 electron process because the oxidation number is changing by 2. Alright, so we have this situation where we have 1 electron in the change in the chromium and 2 electron change for nitric acid, so we have to double the coefficients in front of chromium to balance the electrons. Now the other situation we have, which is similar to what we did at the beginning of class on Friday, March 25th, which is today, as I record this. So we have, in our product, we also have some nitrates, NO3 minuses, as associated with chromium, which still have the same +5 oxidation number that they started with in the reactant side. So because of that, just like we saw in class, what's convenient to do is to split them up. So our chromium chloride, we double the coefficient because we need 2 electrons coming from that. We have 1 HNO3, which is changing its oxidation number, and we'll have a second batch of HNO3, which is just losing the proton to become nitrate. And then our products, we have 2 chromium nitrates, plus 3 though. And then we have a HNO2, so we only need 1 of those because that's a 2 electron process. And then we have plus water plus HCl, so a lot of things to balance now. Well, we've balanced the electrons by putting a coefficient of 2 here and 2 here, and then we want to set this to be 1, the first nitric acid, which is changing its oxidation number. We set that to 1, we set that to 1. So our electrons are balanced, so the rest we just balance by inspection. So on our product side, we have 6 nitrate anions, 2 chromium nitrates, each with 3, so we need another 6 HNO3s. And then to balance the water in the HCl. So if we look at HCl, we have 4 chlorines on the reactant side, so we need 4 HCls to form as products. And then water is a little bit tricky here, but we have a total of all of these nitrates are keeping their oxygen, so this 1 HNO3 is losing an oxygen to become H2O, so we're just going to leave the coefficient of H2O as 1 to make sure that oxygen is balanced. So if we combine the coefficients that are grouped together, it's going to be 2CrCl2, 2 chromium chloride, plus 7 HNO3, plus 2 chromium nitrate, and then HNO2, 1 of those, 1 water, and 4 HCl. So that's the full balancing. What we're asked for is the sum of the coefficients on the reactant side, so it's going to be 2 plus 7, which is 9. So just like we saw in the example in class, when you're balancing reactions like this where, for in this case nitric acid again, where some of it is changing its oxidation number, some of it is just losing a proton, it's helpful to balance them in pieces. As if you try to come up with this coefficient of 7 here, by itself, it would have been very difficult to do. All right, so that's another example of balancing redox reactions, and I encourage you to review all these topics on your own, but certainly come and find me with any other questions you have as you finish your last-minute preparations for the exam. All right, until next time, have a good one.